Okay, hello everybody. So this is the day 5 material. It's the last thing you've got to know. So let's get to it. So what we're doing now is you guys are solving rational inequalities. So you've got a rational expression, another rational expression. The big deal here is it's really hard to figure out when one rational expression is less than another rational expression. They're both variables. They both could equal whatever at any time. So the best way to go about doing this is actually to bring these two rational expressions together, get one side equal to 0, so that you just have a single rational expression less than or equal to 0. And then you just run a sign test. You check to see if that one rational expression is positive or negative, and then that gives you your solution set. So one thing we're definitely not going to do is we're definitely not going to multiply through by the LCD. Multiplying through by the LCD was great when this was just an equals sign. Multiplying through by the LCD canceled our denominator, gave us a polynomial equation that we could just solve easily. But it's a terrible idea when you're looking at an inequality. Because if you multiply through by x plus 1, we talked about how x plus 1, well, this thing is positive for x's that are greater than negative 1, but it's negative for x's that are less than negative 1. And if you try to multiply through by an expression that's negative, then you'd have to flip your sign. So doing that, you could do it, but you'd have to then remember to basically set up two cases. One case where, you'd have blah, blah, blah. You'd have to flip the sign, and it would be greater than or equal to blah, blah, blah. Then you'd have a second case where the thing you've multiplied through by is positive, so you'd have blah, blah, blah is, don't flip the sign, is less than or equal to blah, blah, blah. And then this half of your equation would generate one sort of solution set. This would generate a second solution set, and you'd get there. You'd get to the right answer. But I don't really feel like I'm trying to do all that. So I think the better plan is definitely still just to subtract one of these. It doesn't actually matter which way you go. If I subtract this from both sides, then I'll have blah 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 is less than or equal to 0, meaning we'll be looking for the parts where our function is negative. If I subtract this one, then I'll have 0 is less than or equal to our function, basically meaning our function is greater than or equal to 0, so our function is positive. Doesn't matter which way you go. Either way you go, you'll be able to get an answer. So anyway, without more chit chat, let's just get down to it. I'm going to keep the 1 over x plus 1 over here. I'll subtract the 1 over x minus 3. And so we're here now. But now we got to get these two expressions together. And to bring them together means we need a common denominator. So that means I'll need an x minus 3 in this term. But if I'm multiplying the bottom by that, I'll multiply the top by that too. So I'm going to multiply by that. That'll generate my common denominator. Now the other one, it's missing a factor of x plus 1. So we'll multiply it by x plus 1 over x plus 1. And then that's getting a little messy. That's okay. So what do we got? We're going to have one big fraction that has x minus 3 and x plus 1 in its denominator. In its numerator, we've got an x minus 3. And then we've got a negative 1 that would distribute in here too, so it'll be minus x minus 1. And all that's supposed to be less than or equal to 0. So this one happens to clean up pretty nicely. The x's cancel. You get negative 4. Over x minus 3x plus 1. Now from here we could go ahead and just build our sign chart. If you don't feel like having a negative here, you could multiply through by negative 1, turning this into a positive, flipping the sign, and that would be fine. You'd build your sign chart now using this expression, and you'd be looking for the regions that are positive. It doesn't matter. It's just when you go to build your sign chart, if you do leave this thing negative, then you'll have to take that negative into account as you do all your tests. But basically you'll just have a numerator that's always negative, and then in the denominator you'll test these other two guys. So maybe they're both negative. You'll have 3 negatives, you'll be negative. So I'm inclined to just leave it. I'll just let the 4 be negative and I'll incorporate that into my sign test. So anyway, we can now take this number line that we were provided with. We can mark our zeros, except we don't actually have any zeros. The zeros would come from the numerator. We don't have any. So the zeros of the denominator, they're critical values for us that we'll plot, but they're not zeros, they're points at which we're undefined. So positive 3 is a critical value. We'll mark it. But it's not a 0, so I'll mark it with a U, reminding myself that it's a point at which we are undefined, rather than a point at which we are 0. Negative 1 is another critical value, but it's not a 0, it's a point at which we are undefined. And then this now sort of divides the number line. We've got 3 regions, so you're going to want to test these 3 regions. This thing goes on forever to infinity, this thing goes on forever to negative infinity. So these are my 3 regions, and I'll test them. So we said, basically we've got a negative in the numerator, and in the denominator we got to test these 2 expressions. So you pick any number less than negative 1, doesn't matter what it is. But if I'm less than negative 1 and you take away 3, I'm going to be negative. If I'm less than negative 1 and you add 1, well, adding 1 isn't enough. It would still be negative. And then 3 negatives gives us an overall value that will be negative. Okay, now we check this interval. We've still got our negative 4 in the numerator, so that counts as a factor that is negative. X minus 3, we're still less than 3, so taking away 3 means we will be negative. Adding 1, well, we're bigger than negative 1, so adding 1 is big enough now to make us positive. So we have an even number of negatives, so we'll be positive in this interval. Then over here, we'll have a negative in the numerator. If we're taking away 3, well, we're bigger than 3, so taking away 3 means we'll be positive. Adding 1, well, again, we're bigger than 3, so 3 plus 1 is still going to be positive. So we're back to being negative on that interval. And that's it. There's your whole sign test. You've got all that info now. And we can see from this expression that we're basically trying to figure out when this thing is less than or equal to 0. That means negative, so we'll take the 2 negative intervals. Notice we can also be 0. So we'll say x is an element of the set that contains negative infinity up to negative 1. What have I done? Wrong symbol. We're going to go negative infinity up to negative 1. Now if this was a 0, we'd include it. We'd put a hard bracket. But remember, we're not 0 here. We're undefined. So even though we can equal 0, this should still be a soft bracket because negative 1 isn't a 0. It's a vertical asymptote. It's a point where we don't exist at all. So you can now do the union of that with the interval that goes from 3 to infinity. And again, 3 is not a 0, so don't actually include it. And that would be your solution set. That's it. That's that whole process. Move that over. My head's too big. I'm going to shrink this. I'm going to change the camera angle too. Go on. Hello. There's me. Alright, get shrunk, bro. There we go. Alright, moving on. Alright, number 2. So number 2 looks nice and easy, but we're still greater than 1. And we can't be greater than 1. We got to be greater than 0. Our whole process is kind of predicated on the fact that we just have a single rational expression that's greater than 0. That's the deal. One of our sides has to be 0, or else our approach falls apart. So as nice as this might look, we need to take it and mess it up. So okay, let's just bring it down for now. 2x squared minus 4 all over x squared plus 1 minus 1 is greater than 0. Alright, now we can go to town. But you know, we've got 2 separate terms here, and that doesn't fly. We've got to bring these terms together and just have one term. And to do that, we need a common denominator. So this 1 is really going to want to be 1 over 1, would multiply by x squared plus 1 over x squared plus 1. And that whole thing is just going to become x squared plus 1 over x squared plus 1. Now over here, I got to clean this up too. By clean this up, I mean distribute this too, because we need to expand all that out to get the separate terms so that we can combine like terms with the other guy. So this will be 2x squared minus 8. And all that's supposed to be greater than or equal to 0. Anyway, now we can go ahead and build our big fat fraction. So our denominator is x squared plus 1. Our numerator is 2x squared minus 8. Then it'll be minus x squared. And it'll be minus 1, because you got to basically treat this like it's in parentheses. We're subtracting this whole thing. So we're subtracting x squared, and we're subtracting 1. So make sure that negative sign essentially gets distributed in. But we're here now. So here we can combine like terms, and then we want to factor if we can. So this is x squared minus 9. Once you clean all that up. So x squared minus 9 is a difference of squares, so that'll factor to x plus 3, x minus 3. Now our denominator, on the other hand, doesn't factor. It's x squared plus 1. And even if you tried to solve that, if you tried to find its roots, then you'd subtract 1. And you get x equals plus or minus the square root of negative 1, aka plus or minus I. So since this thing's roots are imaginary, they're not even going to be critical values for us. We won't even write them on the number line because, well, this is the real number line. And these are non-real answers. You literally cannot plot them on the real number line. They're not even part of it. So that denominator kind of plays no role in this problem, really. So let's just take the critical values that we do have, place them on this here number line. I guess I better go up here because I need room. So we'll go there. That looks small and stuff too, but it's not that small, right? All right. So that means our only real valued zeros are at negative 3, and it's a 0, so mark it Z. There's another one at positive 3, mark it Z. And that's it. So I really only have to consider these 3 intervals. The interval of stuff that's less than negative 3, the interval of stuff between negative 3 and 3, and the interval of stuff that's greater than 3. So that should be easy. By the way, this denominator is just always positive. X squared is always positive, and a positive thing plus 1 will be always positive. So I truly can just kind of ignore it, but I won't. We'll build it into our little test anyway, but my denominator is going to be positive. You can just show that it's positive. Then the x plus 3, I'm adding 3, but I'm less than negative 3, so adding 3 isn't enough. I'll still be negative. And of course, taking 3 away from something that's already negative will be negative. But 2 negatives make a positive, so in this interval, we're going to be positive. In the middle, we'll still have a positive denominator. Now adding 3, if I'm bigger than negative 3, then adding 3 will make me positive. Taking 3 away, though, will keep me negative. So we have 1 negative, so in this interval will be negative. And if I'm bigger than 3, then adding 3, I'm positive. Even if you try to take away 3, I'll still be positive. And our denominator is always positive. So we're positive. So our sign test goes plus minus plus again, based on our inequality, I should say, not our equation, but we're saying we want the function to be greater than 0, so we're looking for those positive guys. So we'll say x is an element of the interval that goes from negative infinity up to negative 3. Now this time negative 3 is a 0, but we can't equal 0, so this is going to be a soft bracket again. We'll go union. And then we're not positive again until we get to 3, so we'll go 3 to infinity. Again, 3 is a 0, but zeros aren't allowed, so soft bracket. And that's our solution set. It is in your best interest to consider how this would change if this changed, because obviously, you know, I can do whatever I want when the quiz rolls around, so it might not be strictly greater than. So just for the sake of argument, if we had said, what about if we said the function was greater than or equal to 0, then the only change would go negative infinity to negative 3, and we would include it. It would just go to hard bracket. The other one would go to hard bracket too, 3 to infinity. So not super interesting. Just those would just change, and that'd be fine. I assume you guys understand that just fine. So that's 2. Moving on to 3. All right, here's 3. 3 seems like more of the same. Yeah, either way, I got to subtract one of these terms from both sides. If I go this way, then we'll be negative. If I go this way, we'll be positive. Let's try to do that for a change of pace. Let's subtract this guy from both sides. So we end up with 0 is less than or equal to x minus 1 over x minus 2 minus x plus 2 over x plus 3. So now you got to clean this up. Sure. So let's just do this. This will need an x plus 3 over x plus 3. If we multiply by that, we can start to generate our common denominator. This will need x minus 2. And if we do all that, we'll have 0 less than or equal to, we'll have big fat fraction whose denominator is x minus 2x plus 3. In the numerator, you'll expand this out. You'll get x squared plus 3x minus x, so plus 2x minus 3. X squared plus 2x minus 3. Then don't forget you got a minus sign here, so it'll be minus this whole thing expanded out. That'll just be what? X squared minus 4. But you got to distribute the negative onto that. So after cleaning this up, you'll have 0 is less than or equal to x squared minus x squared. So I guess those x squareds cancel. Okay, so you'll just have 2x and a negative 3 plus 4, so plus 1. Over x minus 2x plus 3. So I think that's it. I think that brings us to our, one single rational expression. It's greater than 0. So we can go to our number line now and start plotting. That should be plenty of room. I'm tired. It's almost midnight. So okay, if you set this equal to 0 and solve, then you'd go minus 1 divided by 2. So negative a half is one of our zeros. Negative a half would go here. Just because it's not marked on the number line, you can just put it there. So negative a half is on the number line now. And it's one of our zeros, so we'll mark it. It truly is a 0, so we'll mark it with a Z. Then, at positive 2, we have a critical value, but it's not a 0. It's a point where we're undefined. And at negative 3, we have a critical value. That is another point where we are undefined. So based on all this, shrunk, 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 I'm seeing 1, 2, 3, 4 intervals that we need to test. I really wish these lines had arrows on the end. So put those arrows on the end, whatever. But again, I see 1, 2, 3, 4 intervals we got to test, so let's test them. So basically our little dealio, there's a factor over a factor times a factor. So again, we'll check all of these things for plus minus, plus minus, plus minus, and evaluate. So on this interval where I'm, all the way left, it's probably safe to say basically always that in this region everything will be negative. It'll be negative. Well, no, it's not safe to say that, because if anything is squared, then something squared is always positive. So I guess it's not safe for me to say this. But in this case, if I'm way the heck to the left, then this will be negative, this will be negative, everything's negative. And so I end up with an overall negative result. Now between -3 and -1/2, adding 3 is now adding enough to ensure that that guy's positive. But I think the other two still stay negative. We're still taking away 2 from a thing that's already negative, so that'll certainly be negative. Here we're doubling and adding 1, but these numbers are still too negative for this to turn on positive, so that guy's still negative. But 2 negatives make a positive, so this interval is positive. Now the second I'm greater than -1/2, now this thing is going to come out positive, so my numerator is now positive. The x plus 3 is still certainly going to be positive, but the x minus 2 is still going to be negative for an overall negative result. And finally, when you're greater than 2, now the x minus 2 is going to be positive, the x plus 3 is going to be positive, and the 2x plus 1 is going to be positive, so we'll be positive. But there's your whole entire sign chart now completed. And we have set our inequality up this time that our solution set would be the positive regions, because it says here that our stuff should be greater than or equal to 0. So you're looking for the positive regions. And we'll have a slightly more interesting solution set this time, because on this interval we go from -3 to -1/2. And -3 we're undefined, so it'll be a soft bracket, but at -1/2 that's actually a 0. And we can equal 0, so that'll get a hard bracket. And we'll go union. Positive here from 2 to infinity. But 2 is another point where we're undefined, so that'll be soft bracket all the way to infinity. Infinity is always a soft bracket. So at least in this solution set, we have one hard bracket that you had to actually think about, since we were allowed to equal 0. We had that 1, 0 in our solution set that we do have to include. That's it. There's no other zeros. Yeah, no other zeros. So that's it. That'll be our whole solution set. Okay. Hopefully this is making sense. Shrink. Okay. 22 minutes already, huh? For 3 problems. All right, next. Number 4. I did this one in class, at least for one of the periods. But you guys don't listen. That's why you watch these videos, right? Ooh. Mr. S getting feisty. Alright, how do we do this one? I guess I'll probably take these terms and just bring them left. That seems easy enough. So I'll get my x cubed minus 2x plus 1 all over x minus 1. We're going to subtract this, so we'll have minus a half x. Now a half x is just x over 2, so I'm going to simplify it. I'm just going to write x over 2 instead of half x. Then the 1, I need to add 1 to both sides, so I'll now have a plus 1. So I did this problem in period 1. You period 8 kids, maybe you guys didn't ask for it. So if you're in period 8, maybe you never saw this one, but period 1 you guys saw this. But we did it. We've got our 0 now. So now we just have to combine these terms. And so thinking about your LCD, if we were still talking about LCDs, which we're kind of not, our LCD would certainly include the x minus 1. But we've also got a factor of 2, so it'll include the 2 as well. And so looking at this whole first term, the only thing we're missing is that factor of 2. So we can just hit this guy with a 2 over 2 to get that common denominator. This guy's missing the x minus 1. So we'll hit this with x minus 1 over x minus 1. But then this 1 doesn't have either of these. So it's going to need to get multiplied by 2x minus 1 over 2x minus 1. But if I do that, then suddenly everybody will have the same denominator. Everybody's denominator will be 2x minus 1, which means it's big fat fraction time. Our denominator will just be the 2x minus 1. And this guy's numerator will be 2x cubed minus 4x plus 2. Here you've got a negative, so don't forget to distribute it. But you'll get minus x squared plus x. And here you've got a plus. So just distribute the 2. You'll get plus 2x minus 2. So that's good. That's going to be greater than or equal to 0. Yep. I might bust out my highlighter. We've got one lone cubic factor. We've got one lone quadratic factor. Then we've got a linear, another linear, another linear, and then we've got constant. So combine like terms. So we'll have 2x cubed minus x squared. And then all these linear factors, what do we got? Negative 4 plus 1 is negative 3 plus 2 is just negative 1x. Then the whole number parts, the constants, just cancel out, which is good news for us. Because now since the constants canceled out, we see that x, there's a common factor of x. I can just factor out an x, and then this cubic reduces down to a quadratic. And ideally that's a factorable quadratic. And it is. So we're going to have in the numerator a factor of x and a 2x x all over 2x minus 1. Alright, so what does this thing factor to? Well, 2 times negative 1 is negative 2. I'm looking for factors that will give me negative 1. Literally the only factors are 1 and negative 2, or negative 1 and 2. And if I want a negative x, then I'm going to go with these factors. So to get that negative 2 as an outer product, I just need a negative 1. To get 1 as an inner product, I just need a plus 1. So there, I'm factored. And once we've got everything factored, we just hop to the number line, do our sign analysis, and get our answer. So where is that number line? I'm tired. Alright, from the numerator we can see we're going to have 3 zeros, one from each of these factors. One of those zeros is 0 itself. 0 is a 0. We have another 0 at negative 1/2. Again, that's going to be another 0. We have another 0 at positive 1. That's a 0. And then we have one more 0. No, don't call it a 0. It's a point at which we're undefined. It's positive. Wait a minute. No. Okay, fine. So we don't have another one. This is it. And you know what? I'm not going to use this number line because everything's too crushed together. Let's make our own number line. So now that we're making our own number line, we can just put negative 1/2 here, 0 here, 1 over there. Everything's still pretty squished. I could have spread that out more, but this is fine. Anyway, so 0 is a 0 for us. Negative 1/2 is a 0 for us. But it turns out I was wrong. I jumped the gun a little bit. Since these guys cancel, that represents a whole. So 1 is actually a point at which we are undefined. So we can label all that. Now don't forget, we'll get an interval here, interval here, interval here. So there's going to be 1, 2, 3, 4 intervals that we must test. Alright, again, I'm seeing what? Thing times thing times thing all over 2 times thing. So let's talk this through super fast. As I'm testing for sign, a factor of 2 doesn't change anything because a 2 is always positive, and positives don't really affect anything. But by the same token, the x minus 1s, since they cancel out, they don't really do anything either. Because if one of them's positive, they're both positive. And having them both positive means nothing changes. You'll just be positive. And even if they were negative, then they would both be negative, and that would cancel out too. So really, do you need to even include them in your calculation? Not really. The only things that really are going to matter are just these 2 factors here, right? So if you wanted to, if you want to just be testing only those two factors, that's fine. I can't fault you for that. I still think I'm probably just going to include this whole shebang. Maybe not the 2. The 2 I'd leave out for sure. But I think I'll probably be marking, thing divided by thing and checking all that just because it's just the way I like to do it. But mathematically, you guys get that the 2 plays no role and that the repeated factors play no role either. Hopefully you get that. So anyway, what happens when I'm less than negative a half? X will certainly be negative. 2x plus 1 will certainly be negative. X minus 1 will be negative. There'll be a 2. And then there'll be another factor that's negative. The 2 literally does nothing. Don't include the 2. But this is an even number of negatives, so we'll be positive. Now once I'm bigger than negative a half, the 2x plus 1 will be positive. But the x will still be negative. So we're going to go negative, positive. The x minus 1 will still be negative as well. But this is still an odd number of negatives, so we'll be negative. Once we are greater than 0, this x term will now be positive, so we'll go positive. 2x plus 1 will be positive. X minus 1, since we're less than 1, will still be negative. But again, there's 2 negatives there, they cancel, we're still going to be positive. We could have been ignoring these things, remember. Alright, finally, once we're bigger than 1, every single factor will be positive, so we're positive. But there's your sign chart built. We go plus, minus, plus, plus, which makes sense. Again, I think I'm finally ready to say that this critical value at 1, since it occurs with an even multiplicity of times, we should be expecting the sign not to change on either side of that. Okay, and it didn't. We got plus, plus. I'm ready to say that now with certainty. So what are we doing? Our solution set is when the function is greater than or equal to 0. So we're looking for all these positive bits. So my solution set then would be x is an element of negative infinity to negative a half. Now I can equal 0, and negative a half is a 0, so that'll get a hard bracket. Now we'll go union. We'll do the next one, 0 to 1. 0 is a 0, so it'll get a hard bracket. But 1 is not a 0. It's a point where we're undefined. So that'll need to get a soft bracket. We'll have to split this into 2 separate intervals because negative 1 is not part of our solution set. So we'll start at 1 and go to infinity. So that's how I see it. Even though we're allowed to equal 0, we're still going to be seeing 3 separate intervals because we can't include the 1. It's not a 0. It's a point where we're undefined. But there's our solution set. So that's that. 1208. Alright, moving on. That was 4. So then we come to 5, which is the one called the Challenger. So I just don't want to do it, honestly. Is it really that challenging though? Not really. The challenging thing is not this. You guys know how to factor this. One thing you may not remember is that 3 minus y, you can just rewrite that as y minus 3, as long as you remember to put a negative sign on it. 3 minus y is the opposite of y minus 3. So once you do that, you should have a handle on what you're doing from there. With that negative, what would I do? That negative makes this whole fraction negative, so maybe I just would be adding that to the other side anyway and subtracting this one. And then you'd have 0 is less than or equal to the 1 minus 5y over y plus 3 plus the y plus 3 over y minus 3. And then this negative now is essentially just gone. By adding this thing to both sides, it just doesn't need to be there anymore. So we just have this now. But this one who's positive, we got to subtract that. So we do get a minus sign. We get 3y plus 1 over y plus 3, y minus 3. So then from here, what would you do? Well, you need this guy needs a factor of y minus 3. So you'll multiply by that on the top and bottom to generate your common denominator. And this factor needs a factor of y plus 3, so you'll multiply by that on the top and bottom. Then from there, everything will have the right denominator. I'm so far through this, I may as well just finish, huh? For your denominator will be y plus 3, y minus 3. Up here, you can expand this out. You'll get, you'll get a y minus 5y squared minus 3 plus 15y. And we'll just clean that up later. We have a y term and a y term. We'll clean them up. We've got a plus sign here now, so we know we can just expand this. This will be y squared plus 6y plus 9. Now here you've got a minus sign, so make sure you distribute that onto both terms. So we're subtracting 3y. And we are also subtracting 1. But there's our whole thing, and 0 is supposed to be less than or equal to that. So we're checking again for when is all this stuff positive. I will bust out my trusty highlighter because I see a quadratic and a quadratic. And I see a whole mess of linear terms, 15, 6, negative 3, and a whole mess of constants, negative 3, 9, 1. Missed one. There's a y. Yeah, alright. So now, 0 is less than or equal to negative 4y squared. Then 16y, 22y, 19y. Alright. And then for the constant, you've got positive 6, positive 5. Okay, all over. Alright, I'm not a huge fan of leading negatives, so as much as I warned you against this, let's go ahead and multiply through by negative 1. And this sign will change, but that's fine, because I'm not multiplying through by a variable expression. I'm multiplying through by a thing that is always negative. So the sign flips, but it doesn't do that thing I was warning you about before. It doesn't generate case 1, case 2, where sometimes I'm multiplying by a thing that's positive. This thing's just always negative. So the whole thing's going to flip just to make it easier to deal with. So we're going to go 0 is greater than or equal to, and now we get a positive leading coefficient now. But this sign will change, and this sign will change. Right? Nothing in the bottom changes because we're really just multiplying by negative 1 over 1. So the negative, as it distributes through the numerator, doesn't disturb anything in the denominator. But this now means we can factor this. 4 times 5, by the way, is 20. And if you want to get a 19, then just use 20 and 1. And if you want a negative 19, you're going to let the 20 be negative and the 1 be positive. So that's our target. So for 4y, we could go 2y and 2y, but 20 is divisible by 2, but 1 isn't. So the 2y ain't going to work. We're going to go 4y and 1y. And then I can get 20, negative 20, by plopping a negative 5 right here. My outer product will be negative 20. If you want 1y, then you'll just let your inner product be positive 1. And then 1 times y will be 1y. So there's my factored form. The negative's gone because we multiplied through by it and flipped the sign, so that's all good. Then in the denominator we've got a y plus 3 and a y minus 3. And now the challenger. It's just not so bad. We're in a place now where we can do this easy. So let's plop these numbers down on the number line. Yoink. We have a 0 at -1/4. And another one at +5. So that's a 0. -1/4 is going to be a 0 for us. -3 is going to be a point at which we are undefined. +3 is going to be a point at which we are undefined. But just like everything else, we go zoomp, 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 zoomp. And we've got our 1, 2, 3, 4, 5 regions. We just test them. And again, I see thing times thing over thing times thing. So we're just going to test each of these factors for plus and minusness. Again, when I'm all the way left, you pretty much always, all of these things will just be negative. And that's the case here too. So I'll go negative, 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 negative. That's going to be positive over positive, which is positive. Okay, in the next region, we are now bigger than -3, which means adding 3 will keep us positive. So this guy flips and becomes positive. All the rest are still going to be negative though, right? Yeah, negative, negative, negative. So now that I have an odd number of negatives, I'm going to be negative. All right, now I'm bigger than -1/4. That means this one now flips and will be positive. So now we've got positive. This guy's still positive, negative, negative. That's an even number of negatives, so we're positive. Now that we're bigger than 3, y -3, this guy will be positive. So all of those are positive. It's only the y -5 that is still negative. And that one factor that's negative causes us to be negative. And then once you're bigger than 5, then this guy will be positive as well. So we'll be plus, 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 which makes the whole thing plus. So sign chart complete. And now it says the way we solved, we're solving for when is the function greater than or equal to 0. So we're solving for positive. So we'll take these 1, 2, 3 intervals. And so our solution set would be x is an element of the set that contains, we're positive from -infinity all the way up to -3. -infinity is never included. -3 won't be included either because we're undefined. We're not 0, we're undefined, so stop bracket. Then we'll go union. The next positive interval is from -1/4 to 3. And this time -1/4 is a 0, so that should be included in our solution set, so it gets a hard bracket. 3, again, we're undefined, so soft bracket. Then we're positive again from 5 to infinity. And again, 5 is our actual 0, so include it in the set. Don't include infinity. So there's the solution set for this one. It'll be these 3 intervals. These 2 intervals are closed on the left, but open on the right. That's it. I think for you guys, that's the end of the road, yeah? But there was a part 2. And I don't think I gave you the part 2. I don't think I did. Was there one with a radical? Anywhere? No. So the only one with a radical that we did was this classwork example. So this is one of the, this is a really good time for you to pause the video. Don't just sit there watching me do this one. You should do this yourself. You guys need this practice. So you could write this down on scrap paper. I'll try to print this out and post it as a PDF that you guys can print if you really want a piece of paper to do this on. But you've seen how to do this already in the classwork problem. So try it yourself. Then unpause the video and check to see how you did. But there's more of these too. So pause the video, try number 6. And I'll show you some more. You can pause the video, try number 7. This one has 2 radicals, so this one I strongly encourage you to try before watching me do it. So pause the video, try this one yourself. Then there's even more apparently. I don't want to do these, but maybe I will. Anyway, there's another practice problem here. It doesn't involve any radicals, but it's, you know, good practice. Here's another one. You guys can do this one if you want to. Here's another one. You guys can work on this one if you want to. Here's another one. And another one. And another and another. None of these are the ones with radicals. I think there's one more. Yeah, so here's another one that has a radical in it. You can do this if you want to. And that's it. Okay. So, you know, I would recommend that you do this. So 7 has the 2 radicals. I would do it if I were you. This 7 has 2 radicals. That's not the same, is it? 4 minus 2x and x plus 11. No, they're definitely different. They're both number 7s, but they're different. Okay, and 6 is different too. So as I click through all this garbage, you guys can see there's a whole bunch of extra practice that you should probably take advantage of. I'm just going to end this video now and make another one, but maybe not tonight. My throat's starting to hurt. So yeah, why don't I do one? I'll do this one here, 6, the one with the radical. If you guys tuned in, that's probably what you've been waiting for. So I'll do this one, but then I'm going to cut this off and post more tomorrow. So how do we do this? Well, same old way, honestly. We see that we've got a 0 at positive 1/2. So we can mark that. We'll mark it as a 0. It's also squared though, so since it's got that multiplicity too, I don't expect my sign to change on either side of it, but we still make a note of the fact that at positive 1/2 we've got a critical value. Negative 3 is a critical value. It is another 0. Apparently positive 12, where the hell over here, is another critical value, and it's a 0. And then 9 is a critical value over here. Now, this doesn't say x minus 9. This says 9 minus x. So it's actually the bigger than 9 values that will make us negative, right? Just think about it. 10. 9 minus 10 is negative 1. This thing is reflected, essentially. So normally with radicals, we would think, you know, it's everything less than a certain value makes us non-real. But here it's actually everything greater. And so that actually means that at 9 we are undefined, but on this interval from 9 to 12 we're non-real. And we haven't seen this before, but when we're bigger than 12 we're non-real too. And so that means that actually 12 isn't a 0, because 12 would cause this radical to be negative. So 12 is not a 0 anymore. Like, scribble that out. It gets overwritten by non-realness. It's in the middle of our non-real interval, so non-realness overwrites everything. That's the thing that takes precedent. So we now know that from 9 to forever we're non-real instead of anything else, but everything else will still test. And so again, I see thing that is squared times thing all over thing. What part of this do we really need to evaluate? Well, because the 2x minus 1 is squared, we know that if it's positive, a positive squared will be positive, but even if it's negative, a negative squared will be positive. So you essentially know that this whole position is just going to always be positive. Does that mean it can safely be ignored? Yes, you could actually just ignore it because it's always positive. Now obviously this thing will be plus or minus, this thing will be plus or minus, but the radical down here, anytime that it's not non-real, it'll be positive. So this is another guy that we could almost kind of ignore. But again, I'm not going to ignore any of it. I'm going to choose to leave it all in there, just because. When I see an expression that clearly has 1, 2, 3 things in the numerator and 1 thing in the bottom, that's just still how I want to tackle it. So let's do that. There was a fly. I missed it. I'm going to leave it alone. Stinking fly. All right. So if I'm less than -3, what's the deal? Well, we just got finished saying that thing's going to be positive for sure because it's squared. If I'm less than -3, then adding 3 is not enough. That factor will be negative. Taking 12 away will obviously be negative. My radical will be positive. So in this region that I haven't actually drawn the columns for, in this region will be positive. Next region, I'm bigger than 3 now, so the x plus 3 will be positive now. The x squared thing will be positive. Taking away 12 though, that won't be positive until we get all the way out here to 12. So that guy's still negative. And the radical's still positive. So it looks like I'm negative on this interval. Now we go from a half all the way to 9. So again, the thing that's squared will be plus. The thing where I'm adding 3 will be plus. The thing where I'm taking away 12 will still be negative. And the radical will still be positive. So in this interval, I'm still negative. And we talked about this. We said the 1/2 is coming from a factor that occurs an even number of times. So it essentially has an even multiplicity. So we should have expected the sign not to change on either side of the 1/2, and it didn't. Now, this whole interval is non-real, so I suppose I don't really have to test what's going on at 12 anymore, because we know we're just going to be non-real everywhere. So don't bother. Non-real, non-real. You don't have to run your sign tests. We can just stop here. So now you got to answer all these questions. So question A wants to know, when are we 0? And the answer is we'll be 0 when x is an element of the set of. We have a 0 at -3, which is safe. We have a 0 at a half, which is safe. And then we thought we had a 0 at 12, but we don't, because we found out that we're actually non-real on that interval instead. So be careful about just blindly giving me all the zeros from the numerator. If there's some radical that will be negative at those values, then they don't count as zeros anymore. So that's that. Part B wants to know, when are we going to be positive? And we're positive here, -infinity to -3. We're positive again, never. So that's it for positive. Now part C is sort of related. It says, when are we non-negative? Which you guys remember means basically find the values of the function when we are greater than or equal to 0. So it should be pretty similar. We're going to be x is an element of, we'll go -infinity up to -3 still. But I can equal 0 now, and so that 3 gets a hard bracket. And maybe more importantly, even in this sea of negativeness, there's a 0 at 1/2. So we'd have to do the whole union with a little singleton value at a half. That's now part of my solution set. Remember that the 12 isn't, though. Even though the 12 appears to be a 0, it's actually living in this non-real interval. So we wouldn't add that as a 0. We would just add this. So that's how it changes from B to C. Now for D, they just want to know, when are we negative? So you just give the two negative intervals. It'll be x is an element of -3 to 1/2. And also 1/2 to 9. Is that it? Yeah. And again, we can't just go from -3 straight to 9, because 1/2 is a 0. We're trying to be strictly negative. So 1/2's not part of our solution set, so you'd have to do two separate intervals where 1/2 is not included in either. For part E, they want to know, when are we undefined? And that's just going to be a couple of places, or just one actually. Just one place, just at 9 itself. So just 9. because that causes division by 0. And then F wants to know, when are we non-real? And we'll be non-real from 9 all the way to 12, and from 12 to infinity. And really we said 12, we're non-real at 12. So this isn't two separate intervals, it's really one smooth interval. Even at 12, we're non-real. Remember, 12 was trying to be a 0, but it's not a 0. It's just a place where we're non-real. So let's just go from 9 all the way to infinity. No indication whatsoever at 12. And that's it. We've addressed everything. We've got the zeros, we've got where are we positive, where are we non-negative, we've got where are we negative, we've got where are we undefined, and we've got where are we non-real. Okay? So that's it. That's basically the end of what you need to know for the quiz. But again, I warn you, there's all these extra practice problems. And you know, again, just roll the video back, click pause or whatever. You could do these, and I'll post a second video about those answers. But I hope this helped, and I'll see you guys on Monday. Come in ready to go. Bye.